Alright, let's go. Number 8. The field, not the particle. In 1964, Peter Higgs was not trying to discover a new particle. He was working through a technical problem in gauge field theory. How could the carriers of the weak nuclear force have mass without breaking a symmetry that quantum field theory required to remain unbroken? At Edinburgh, working alone, he sat with an equation that refused to close. The rule was strict. Any theory that assigned mass directly to the W and Z bosons broke gauge symmetry, and any theory that broke gauge symmetry produced infinities in every calculation. The photon avoided this by being massless. The weak bosons, physicists knew from experiment, were not. Higgs realized the mass didn't need to be inside the particle. It could be in a field that filled all of space, and the particle would gain mass by moving through it. Peter Higgs published this in Physical Review Letters in October 1964, under the title Broken Symmetries and the Masses of Gauge Bosons. François Englert and Robert Brut at the Université Libre de Bruxelles had reached the same conclusion 2 months earlier in the same journal. Gerald Guralnick, Carl Hagen, and Tom Kibble at Imperial College London published a third independent version weeks after Higgs. 3 papers, 1 mechanism. For 48 years, no one could prove the field existed. Direct searches at CERN's LEP collider from 1989 to 2000 came up empty. Fermilab's Tevatron ran until 2011 and never reached the required energy. Theoretical objections piled up. Some physicists argued the field was a mathematical convenience rather than a physical thing. The 2012 detection at the Large Hadron Collider of a 125 giga-electron-volt boson finally confirmed the field's existence, because a boson is the ripple, and a ripple requires the field to ripple in. Everything you have ever called matter is passing through this field right now. It is inside your chest, between your fingers, inside your eyes. You have never felt it. You are made from things that feel it. What is a field made of, if nothing ever detects it directly? The next one asks how long a confirmed theory can wait for its proof. Number 7. The 48-year wait. In 1964, Peter Higgs did not think anyone would ever verify his idea. His paper was almost rejected by the referee at Physics Letters before he added a paragraph mentioning a possible massive scalar particle that might, in principle, be detectable. He included it as a courtesy. He did not expect the detector to be built in his lifetime. Physics predictions usually resolve within a decade or two. Einstein's general relativity was tested within 4 years of its 1915 publication. The neutrino was proposed by Pauli in 1930 and detected by Cowan and Rines in 1956. Antimatter was predicted by Paul Dirac in 1928 and found by Carl Anderson in 1932. Waiting was normal. Waiting nearly 50 years was not. The Higgs boson was announced by CERN on July 4, 2012, 48 years after prediction. Peter Higgs was 83 years old. He wept quietly at the announcement. The Atlas collaboration reported the discovery in Physics Letters B, volume 716, in September 2012. The CMS collaboration published its confirmation in the same issue. The particle appeared at 125 giga-electron volts, produced in proton-proton collisions at the Large Hadron Collider, a 27-kilometer ring beneath the border of France and Switzerland that cost roughly 4.75 billion Swiss francs to construct. Every earlier attempt had failed. LEP, running from 1989 to 2000, ruled out Higgs masses below about 114 giga-electron volts, but could not push further. The Tevatron at Fermilab tried through the 2000s and closed in 2011 with the mass just out of reach. Its final combined analysis reached the window from 115 to 135 giga-electron volts, with insufficient statistics to claim discovery. Between 1964 and 2012, 3 generations of physicists worked on the search. Most who started did not live to see it end. The building that finally found the particle did not exist when the theory was written. The mathematics required a machine that required a civilization that required a century of engineering. How many other confirmed theories are waiting for a machine we have not yet imagined? The search may not even be over. There could be other Higgs fields we haven't caught. Number 6. The missing Higgses. Through the 1970s and 1980s, theorists building supersymmetry, a proposed extension of the Standard Model that pairs every known particle with a heavier partner, kept running into the same requirement. Their equations refused to close with only one Higgs field. Minimal supersymmetric models needed two. Two Higgs doublet extensions required at least 5 distinct Higgs bosons, 2 charged, 2 neutral scalar, and 1 pseudoscalar. The standard model, in its minimal form, requires exactly one Higgs field with one detectable boson. That is the simplest possible arrangement. It works. It matches everything measured so far. The problem is that works and is complete are not the same statement. Several respected extensions of the standard model, supersymmetry, composite Higgs models, 2 Higgs doublet models, all predict additional Higgs particles we should already have detected. John Gugnion, Howard Haber, Gordon Kane, and Sally Dawson cataloged the expected signatures in their 1990 textbook, The Higgs Hunter's Guide, published by Addison Wesley. Their predictions have been the search template ever since. ATLAS and CMS have now excluded charged Higgs bosons, up to roughly 1 tera-electron-volt across most parameter ranges, and heavy neutral Higgs bosons across similar mass windows, with the most recent bounds published in the Journal of High Energy Physics through 2024. Every clean prediction of supersymmetry has failed at the LHC. The lightest supersymmetric partner has not appeared. Extra Higgs bosons have not appeared. Composite Higgs models predicting scalar resonances have found nothing. The theories are not falsified. The extra particles could simply be too heavy for the current machine. But every year without a detection tightens the range where they could still exist, and shrinks the case that the mechanism giving mass to the universe is anything more than the plain single field discovered in 2012. Either physics is simpler than most theorists believed for 40 years, or the deeper structure is hiding just beyond the energy we can currently reach. How do you know a story is complete when your only method of looking is finding things? The next entry rewinds to the moment mass first entered the universe. Number 5. The moment mass began. In 1972, David Kuznets and Andrei Linde, at the Lebedev Physical Institute in Moscow, were studying phase transitions in quantum field theory. They were not trying to describe the early universe. They were working on an abstract question. How does a field's ground state change with temperature? The Higgs field, they realized, behaves like water. At sufficiently high temperature, the field averages to zero everywhere. No direction is preferred. No particle receives mass. Below a critical temperature, the field settles into a non-zero value, and mass switches on for every particle that couples to it. Their calculation implied that in the first instant after the Big Bang, when temperatures exceeded roughly 10 to the 15 Kelvin, nothing had mass, not the electron, not the quarks, not you, in any recognizable form. Mass began later. Kuznets and Linde published this in Physics Letters B, Volume 42, in 1972. Later refinements placed the electro-weak phase transition, the moment the Higgs field settled into its current value of 246 giga-electron-volts, at roughly 100 billionth of a second after the Big Bang. Before that instant, every constituent of your body would have been indistinguishable from light. Physicists have not been able to explain why the transition happened when it did. Attempts to derive the vacuum expectation value of 246 giga-electron-volts from first principles have failed. Attempts to link the timing to inflation, to grand unification, or to symmetry breaking at higher energy scales have all produced consistent scenarios, but no unique answer. The number sits in every equation of the standard model as an input that must be measured, not derived. Your existence traces back to a specific temperature line the universe crossed exactly once. Above that line, the atoms in your body could not have held together. Below it, they could. What was matter, before it had the property we call mass? Even after mass turned on, nobody can explain why it settled at the values it did. Number 4. The coupling nobody can explain. After the 2012 discovery, the ATLAS and CMS teams spent years measuring how strongly each standard model particle interacts with the Higgs field. They had a menu of couplings to test, one for the top quark, one for the bottom, one for the tau lepton, one for the muon, one for the electron. They were doing bookkeeping. They expected patterns. If a single field gives all mass, the simplest expectation is that all particles couple to it with similar strength. That was the pattern nobody found. The couplings turned out to span more than 5 orders of magnitude, and no theory predicted the specific spread they measured. The top quark's coupling to the Higgs is close to 1. The electron's coupling is roughly 3 times 10 to the negative 6, nearly 340,000 times smaller. Same field, same mechanism, completely different response. The combined ATLAS and CMS coupling measurements were published in the Journal of High Energy Physics, Volume 8, in 2016, and updated in Nature in July 2022, on the 10th anniversary of the discovery. The top Yukawa coupling was measured near 0.99. The electron-Yukawa coupling was inferred at approximately 2.94 times 10 to the negative 6. No underlying rule connects the values. Supersymmetry predicted specific coupling relationships. None were observed. Extra-dimensional models predicted geometric hierarchies. The hierarchies did not match the data. String theory landscapes offered so many possible values that they explained nothing at all. Anthropic arguments, that the values must be what they are because otherwise we would not exist, cannot be tested. The pattern has been measured with high precision and remains, in the phrase used in physics colloquia, unaccounted for. Your chemistry depends on the electron's small mass. Your bone density depends on the specific quark masses inside protons. If any of these couplings had been different, atoms would not exist in their current form. Why does one field, applied by one mechanism, produce numbers that follow no pattern anyone has been able to find? The oddity gets worse when you ask why the Higgs mass itself has the value it does. Number 3. The hierarchy problem. In the late 1970s, Leonard Susskind at Stanford, Gerard Hevet at Utrecht, and Kenneth Wilson at Cornell were working through the mathematics of what physicists now call naturalness. The idea that fundamental constants should not require extreme fine-tuning to produce the world we observe. They were formalizing an aesthetic principle. They found something worse. Quantum field theory says that the mass of a scalar particle like the Higgs receives corrections from every heavier particle it can interact with. These corrections should push the Higgs mass upward, not slightly, but toward the highest energy scale in the theory. If nothing intervenes, that scale is the Planck mass, roughly 10 to the 19 gigaelectron volts. The measured Higgs mass is 125 gigaelectron volts, not 10 to the 17 times larger. Not close. The corrections that should have raised it do not appear to have done so, and no known mechanism cancels them. Leonard Suskind's 1979 paper in Physical Review D, Volume 20, Dynamics of Spontaneous Symmetry Breaking in the Weinberg-Salem Theory, stated the problem formally. To keep the Higgs mass where it is measured, the cancellation between quantum corrections and bare mass must occur to roughly 34 decimal places, an accuracy of 1 part in 10 to the 34. Supersymmetry was proposed as a fix. It introduces partner particles, whose corrections cancel the problematic ones exactly. The LHC has searched for supersymmetric partners for over a decade, and found none up to masses that make the cancellation itself require fine-tuning. Extra spatial dimensions were proposed. With the effective Planck scale lowered, no extra dimensions have been detected. Technicolor, which replaced the elementary Higgs with a composite object, was ruled out by the boson's measured properties. The anthropic multiverse suggestion, that our universe is one of many, with the Higgs mass a random draw, cannot be tested. Your existence rests on a number that, according to every calculation, should be 17 orders of magnitude larger than it is. When a value requires 34 decimal places of luck, is luck still an explanation? The strangeness deepens when you consider where your own mass actually comes from. Number 2. The mass that isn't inside you. In the 1960s, as the Higgs mechanism was being formalized, physicists began asking a question that sounds childlike, but has no simple answer. Where is the mass of a proton? Is it inside the quarks? Between them? Distributed across the field? The math was clear. The physical picture was not. Your intuition says mass is a property of the stuff you are made from. A brick weighs what it weighs because there is a brick's worth of material inside it. That picture is close to entirely wrong for the atoms making up your body. Lattice QCD calculations, performed at institutions including Jefferson Lab in Virginia and the Riken Center in Japan, have shown that roughly 99% of the mass of a proton comes not from the Higgs field, but from the binding energy of quarks and gluons held together by the strong force. The Higgs contributes only about 1%. The proton mass is 938.272 megaelectron volts. The three constituent quark rest masses, from Higgs coupling, total only about 9 megaelectron volts. The remaining 929 megaelectron volts comes from E equals mc squared, applied to the internal motion and confinement energy of the quarks and gluons trapped inside. The electron, however, is different. Its 0.511 megaelectron volts of mass come almost entirely from the Higgs field. Attempts to build an intuitive picture of what coupling to a field physically means have all failed. Analogies to swimmers in water, celebrities pushing through crowds, and cars slowing in traffic each capture one aspect of the mathematics and mislead about several others. No visualization survives contact with the equations. What remains is the number. Your bones hold their length because electrons have the small mass they do. Change that coupling, and every atom in your body changes size. Your body's shape is a consequence of a field you have never touched. What are you, structurally, without the field you cannot feel? And that field, the one giving you shape, may be sitting somewhere it should not. Number 1. The metastable vacuum. After the Higgs mass was measured at 125 giga-electron volts in 2012, several groups immediately began asking what that specific number implied for the stability of empty space. They were not trying to find an existential problem. They were checking a calculation. The calculation returned a result that has not been comfortably resolved since. A physical system is stable when it sits in the lowest possible energy configuration. The Higgs field, at its current value of 246 giga-electron volts, should be at the bottom of a potential well. If the well is a true minimum, the vacuum of our universe is safe. If it is a false minimum, a shallow dip with a deeper valley elsewhere, the vacuum could, in principle, tunnel through the barrier to the true minimum, and physics as we know it would change everywhere the transition swept. The measured Higgs mass, combined with the measured top quark mass of 173 giga-electron volts, places our vacuum near the boundary between stable and unstable. Not comfortably inside stable, near the edge. Giuseppe de Grassi, Stefano di Vita, Joan Elias Miro, Jose Espinoza, Gian Giudice, Gino Isidori, and Alessandro Strumia calculated this in a paper published in the Journal of High Energy Physics, Volume 8, in 2012, titled Higgs Mass and Vacuum Stability in the Standard Model at NNLO. A follow-up by Dario Butuzzo and collaborators in the same journal in 2013 refined the position. Our vacuum sits in a metastable region, technically unstable, with a predicted decay time vastly longer than the current age of the universe. The long decay time offers less comfort than it sounds. The estimate assumes no unknown physics changes the calculation, and it does not explain why the numbers landed near the edge at all. Supersymmetry could rescue the situation, but has not been found. Extra fields could stabilize the potential, but have not been observed. Sidney Coleman's 1977 paper in Physical Review D, Fate of the False Vacuum, showed that if such a transition ever nucleates a bubble somewhere in space, it would expand at the speed of light. No signal would precede it. Every atom in your body sits inside a field that our best measurements say is sitting in a valley that may not be the deepest one available. The transition, if it comes, is not something you would see approaching. Why does the mass of the particle that shapes reality land, of every possible value it could have taken, near the exact boundary at which reality is no longer guaranteed to hold? Every entry on this list sits not at the outer edge of physics, but at the center of the theory that best describes reality. The Higgs mechanism has been confirmed. Its consequences have not been understood. Mass, stability, the values the universe chose, each measured with extraordinary precision and explained by no one. The field that lets you exist does not tell you why. If you want to see more videos like this, click the video on screen now.